I reproduced the essential formulas which are needed for our future progress. And I changed our new parameter to some integer n. Now I leave it up to you to prove that if n is negative or 0, then we encounter the same kind of problem than we had before, namely at large positive or negative values of y, we get the same blowing up solution. So negative n or even non-positive n are not an option for our case. So let's consider the case of strictly positive n. So n equals 1, 2, and so on. This way we see that our phi function doesn't have a pole at t equal to 0, and the whole integrand becomes an analytic function in a complex plane. So as a contour, we may choose again the vertical infinite segment. However, now the integral became much simpler, and indeed we'll learn in a second that it can be reduced to polynomial. So let's see how it comes about. Well, first of all, for convenience, we can shift the contour in any way in a complex plane, and let's actually position it in such a way that it coincides with the imaginary axis of the complex variable t. This way the integral becomes from minus I infinity to plus I infinity over the same integrand. Now we may switch to a more suitable integration variable. Namely, we can, looking at the exponent function, as usual, we can detach a full square. And let's make a suitable change. T plus 2y equals to, say, is. This way, the integral becomes from minus infinity to plus infinity, e to minus s squared over 4 times is minus 2y times n minus 1 times I ds. So after the change of variables, you see that the only y dependence in our integrand is located in the pre-exponential factor. And the integral actually can be taken exactly for arbitrary value of integer value of n. And I leave it up to you as a homework exercise to prove that this integral indeed gives you the correct Hermite polynomials, although here I dropped the additional exponent function, exponential function, e to minus y squared. So this integral is proportional to hn of y. And as a result, the entire solution now, taking into account this exponentially decaying factor, is just e to minus y squared over 2 times the Hermite polynomial of y. So as you see, this treatment is slightly different, because before we recovered the Hermite polynomials as a closed contour integral in a complex plane. Here, however, it's an integral along the infinite segment, and the whole procedure looks slightly different. So this was the key idea behind this exercise, to show that the same kind of logic works, but the picture and the structure of the contour is entirely different now in a complex plane. That's it.